In the previous video, we have created a peripheral class, and now we need to make sure it accesses proper memory addresses in our microcontroller. Let me show you how to do this. Before we start, I would like to remind you that there is a repository with a source code for this video available on my GitHub. Also, please remember this is a part 2 video about peripherals and classes, and I highly recommend watching part 1 if you didn't watch it yet. As we know, our Cortex-M based chip has memory mapped peripherals, and it means that every special function register has a predefined address in memory space. This also means that if you want to control peripherals using own implemented classes, we need to place instances of these classes at memory addresses fixed to peripherals. The question is, how do we make sure an object is placed at a predefined address? There are a few possibilities how to do it, and in this video we will cover so-called reference placement. What does reference placement mean? Well, basically we are saying to compiler, hey man, treat this part of memory as an instance of this class, and here give me a reference to that object. Sounds easy, right? And it is easy. With a single line of code, we can get a reference to memory mapped device, and thanks to methods that we defined inside our class, we can make operations on registers and control peripherals. Analyzing from the right side, we have an integer, which is an actual peripheral address. Now we cast this integer to a pointer to Gpio type and dereference it. The referenced object is what the reference binds to. Now, having such reference, we practically treat it like an object, and so we can call methods and modify its members. For example, we have a user key switch which is connected to a pin A0. To handle the switch, let's configure this pin to input mode with pull-up resistor enabled. For this, we need to implement some additional things. First, let's add an enum class for pull-up and down setting. Additionally, let's add a function that takes two parameters and operates on pull-up, pull-down register. First parameter is a pin which it concerns, and second parameter is a pull configuration for this pin. Inside this function, we do exactly the same operation as we did when implementing setPinMode function. And so we take the POPDR register value, then we clear the 2 bits responsible for setting pull-up and down configuration of the selected pin, and finally, we set a new configuration for this pin. All this without modifying configuration of other pins. Last thing that we need is a function to read pin input state. By reading an input data register and applying a proper bit mask, we can get a value representing a pin state. If the value is equal to 0, then it means our input is low or logic 0, so we return false. And if the value is not equal to 0, then the input is high, and so we return true. Using our new functionalities, we can refactor our application from Gpio inputs video. Let's use the reference and replace all the lines of code handling PA0 input. We can also replace all the lines of code handling PC13 output. For this, we need some additional functions in our Gpio class, and that is setPushPullType, setSpeed, setPin, and resetPin. And of course, we also need enums for output type and speed options. Let's set pin 13 to output, set this output to push-pull type, and set its speed to low. Of course, we must also set output to high or low, depending on input state. Quick build and board reflashing, and we got again the same functionality, but this time with a nice C++ style code. Let me know in the comment section what do you think about the presented approach. Do you see any issues in this solution? Feedback much appreciated. In future videos, I will show you what can we do with encapsulated peripherals. In the meantime, you can have a look on my GitHub repository with Blackpill source code and already check what are the possibilities. Thanks for watching and see you next time.